When you look at the back of, like, a vintage mechanical watch, you can see exactly why the hands are moving.
Yeah, you can see every single gear in there.
Exactly.
Yeah.
There's a gear turning another gear. The tension is slowly releasing from a spring. It's entirely visible cause and effect. You never have to guess what the watch is thinking.
Right, there's no mystery to it.
But then you open up your laptop and you type a really complex philosophical question into one of today's advanced AIs. And it spits back this perfectly reasoned, deeply insightful essay in like 5 seconds.
And suddenly that transparent clockwork is just totally gone.
Totally gone. We are staring into a black box, and everyone from theoretical physicists to philosophers to software engineers is standing around arguing about it. Like, does this machine actually understand what it's saying? Or is it just a very, very convincing parrot?
That is the million-dollar question right now.
It really is. So welcome to another deep dive. Today, we've designed a custom journey specifically for you, the learner. If you want to cut through the noise and the hype and, well, the incredibly dense jargon surrounding artificial intelligence, you are exactly who we built this conversation for.
We have some really fascinating source material to get through today.
We do. Our mission today is to unpack a brilliant and, frankly, groundbreaking scholarly article. This is from May 2026 by Dr. Raul Michelini from Mindful Machines and the Mindful AI Foundation.
It's a fantastic paper.
Yeah, and this paper aims to completely redefine what intelligence actually is. It's pushing us away from this current obsession with just generating text and moving us toward a rigorous engineering concept called governed representation.
Right, because the reason everyone is arguing about whether AI truly understands anything and the reason it feels like no one can agree is because these different disciplines are fundamentally talking past each other.
Oh, completely.
What's fascinating here is that computer scientists, linguists, and philosophers are using the exact same words to describe totally different phenomena. They are confusing basic concepts like data, information, meaning, and knowledge.
They just throw those words around interchangeably.
Exactly. And the core problem this paper identifies is that reality isn't just a static pile of data waiting around to be extracted by a computer.
Right.
Reality is an open, constantly changing structure. It presents constraints and surprises and actual physical consequences. For any finite system to survive, whether that's a biological organism, a human society, or an artificial intelligence, it has to take signals from that changing reality and use them to test and update its internal models.
Because if a system's internal model diverges from actual reality, that system eventually breaks down.
Exactly, it fails.
Okay, let's unpack this. Because to understand why our current AI struggles with reality, the paper says we first have to understand the specific vocabulary of how any system processes reality.
Yes, Dr. Michelini lays out a very specific progression here.
Right, it goes data, signal, information, meaning, and knowledge. Let me try an analogy here, just to see if I am grasping the mechanical difference. Let's say a weather radar sends out a ping, and it bounces off a storm cloud.
Okay, I like where this is going.
So that raw recorded bounce, that's just data, right? Or
Yeah.
like a signal crossing a boundary.
Yes, exactly.
But it only becomes information or meaning if that radar ping hits a receiver at the National Weather Service. And the receiver actually has the prior knowledge to realize, oh, it's a supercell, and then uses it to issue a tornado warning. Is that the dividing line?
The radar ping is a really good starting point, but we need to look closer at the receiver's internal state to truly separate those terms.
Okay, how so?
Well, the paper defines data simply as recorded differences, not necessarily meaningful, just recorded. A signal is a structured perturbation crossing a boundary like your radar wave hitting the dish.
Right.
But drawing on Burgeon's general theory of information, the paper insists that information is not some universal substance just floating in the air. Information is specifically the capacity of a signal to change a receiving system.
Oh, wow. So it has to actually cause a change.
Yes. Meaning, then, is the interpreted consequence of that change. It is the difference the signal makes for future action.
So the meaning is what you do with it.
Exactly. And finally, knowledge is when that epistemic structure is stabilized into a revisable policy. The Weather Service doesn't just react to one storm, right? It updates its entire forecasting model based on that storm's behavior so it can act coherently tomorrow.
Man, it drives me crazy that tech companies keep telling us these AI models know things when they're clearly just swapping signals around. How did computer science get this entire progression so wrong in the first place?
We really have to look at the foundation of modern computing for that, specifically the work of Alan Turing and Claude Shannon in the mid-20th century.
Right, the pioneers.
Yeah. Shannon gave us the mathematical theory of communication. Basically, how to transmit a signal over a noisy channel, like sending a telegram. But to make his math work, Shannon intentionally bracketed out semantic meaning.
Wait, really? He just ignored it?
He explicitly stated that the semantic aspects of communication are irrelevant to the engineering problem. He just needed the bits to arrive intact. He didn't care if the message was a grocery list or, a declaration of war.
Wow.
And Turing formalized computation in a similar way, focusing purely on manipulating symbols according to rules. Their brilliant work made modern hardware possible, obviously, but it accidentally birthed a culture that conflates symbol manipulation with actual intelligence.
So we built an entire industry that forgot the symbols were supposed to actually point to something real.
Precisely.
If true knowledge requires translating signals into actual meaning, how do systems practically do that? Because the paper argues there are two primary protocols systems use to navigate reality, right? Mathematics and language.
Yes, and the author treats them as distinct epistemic protocols, not just abstract concepts. Let's look at mathematics first. We often hear math casually called the language of nature.
Sure, yeah.
But this paper argues it's better understood as a formal protocol for preserving structural invariance. Math is powerful precisely because it selectively ignores irrelevant details. It creates a formal representation that locks in stable relationships, symmetries, and quantities.
It's like how a subway map works, right? It ignores the exact geographical curves of the streets above ground, the trees, the traffic lights.
Exactly.
It ignores all that detail to perfectly preserve the topological connections between the stations. You don't need the geography to know which train to take, you just need the structural relationship.
That's the exact mechanism at play. Mathematics gives you a rigid, verifiable structure. But language operates under completely different mechanics.
Because language is messy.
Very messy. Language is an interpretive protocol. It's optimized for communication, social coordination, and negotiating meaning among agents who have entirely different prior knowledge.
Right.
The paper draws heavily on philosophers like Wittgenstein and Peirce, here to explain why language is so tricky for computers. Meaning isn't contained inside a word the way, water is contained in a glass.
Meaning is a triadic relation, right? The paper breaks it down into the sign, the object it refers to, and the interpretant.
Yes, that's Peirce's semiotics.
So the word dog is just a sign. The object is the actual furry animal in the physical world. And the interpretant is the mental concept the receiver reconstructs in their head. The word dog only means something because I have physical experience with actual dogs.
Exactly. And this is where Dr. Michelini introduces a formal knowledge update formula. He argues that language doesn't just passively transmit facts.
Okay, what's the formula?
He proposes that the change in a receiver's knowledge is a mathematical function of several variables. It depends on the message, their prior knowledge, the context, the protocol being used, governance or trust, and embodied experience. Language relies on the receiver's context to actively alter their internal structure.
Wait, if language is an update function, then when I ask a large language model a question and it generates a confident, beautifully written sentence, it isn't just spitting out a static output.
No, it is not.
According to this framework, that AI is performing an epistemic intervention on my brain. It is actively rewriting my prior knowledge. And that sounds incredibly dangerous if the AI doesn't actually understand context or truth or trust.
This raises a massive question, and it's the exact systemic vulnerability the paper is highlighting. A large language model is a statistical engine.
Right.
It can generate linguistically plausible signals because it has mapped the probabilities of which words follow other words. But it generates those signals entirely without the internal grounding, the embodied experience, or the commitments that make those signals truly meaningful.
It just has the signs.
Exactly. It possesses the sign, but it has no contact with the object or the interpretant. Yet, because it speaks so fluently, it triggers a knowledge update in you, the human receiver.
So, what does this all mean? If an AI is constantly performing interventions on our knowledge without actually being grounded in reality, there has to be a breaking point.
There absolutely is.
And the paper gives us a very specific term for this, which might be the most important metric of the whole deep dive: coherence debt.
Coherence debt is a brilliant unifying concept for the failures we're seeing in modern AI. It is defined as the accumulated divergence between a system's internal representations, its declared commitments, its actual behavior, and the evolving reality in which it operates.
It's like, imagine you're using a GPS app. The voice is calm, it's confident and fluent. It gives you perfect turn-by-turn directions, turn left in 100 feet.
Right?
But it is directing you straight into a lake. It is locally fluent, like the audio output sounds perfect, but it has massive coherence debt because its internal map has completely diverged from the physical reality of the world.
That is exactly it. The system is optimizing for local outputs, like giving you a fluent verbal instruction while silently accumulating systemic risk.
It's terrifying.
It is. In physics, coherence debt happens when a theoretical model works perfectly on a chalkboard but falls apart when tested under new boundary conditions at quantum scales. In the realm of AI and LLMs, this debt manifests as what the industry calls hallucinations.
When it just makes things up.
Right. The AI provides a fluent output without any warrant. It writes a legal brief citing entirely fabricated court cases.
And because it sounds so confident, a human lawyer actually files it in court, reality pushes back, and the whole illusion comes crashing down. But, like, why can't we just program the AI to double-check its work?
Traditionally, computer science has tried to solve this problem by applying external governance. Think about the von Neumann architecture, which runs almost all our modern software.
Okay.
In a von Neumann machine, the physical processor that executes the code is completely separate from the memory and the governance of the system. We build the application, and then we build separate external software like monitors, antivirus logs, and human oversight committees to watch the application and make sure it behaves.
So we keep trying to put higher and higher guardrails around the black box.
Exactly. But the problem is that in open, unpredictable environments, external governance is simply too slow and disconnected. The system generates language and causes epistemic interventions far faster than external monitors can verify them.
Wow.
If the AI does not internally possess an immutable model of its own commitments, the coherence debt will eventually bankrupt it.
So if external guardrails are failing to stop this coherence debt, we can't just keep building thicker guardrails. How do we actually change the core of the AI itself?
This is where Dr. Michelini shifts from diagnosis to engineering.
Right, he doesn't just diagnose the disease. He proposes a fundamental engineering shift to what he calls mindful machines. Now, we need to be careful with the vocabulary here. The paper explicitly states this is not about machines suddenly waking up, becoming sentient, or getting human consciousness right.
Correct. The term mindful here is strictly an engineering designation. It refers to engineering machines with the intrinsic capacity to maintain their commitments, to track their own history, and to actively self-correct when they sense their internal models diverging from reality.
How does that actually work mechanically? The paper introduces something called the Digital Genome. Is that like a separate database, a line of code? How does the digital genome physically stop an AI from hallucinating a fake lawsuit?
Think of the digital genome as an immutable framework of operational constraints and systemic purpose, but it's encoded directly into the system's core architecture, not bolted on as an afterthought.
Okay.
It defines the system's identity and its stored boundaries, and alongside this genome, the architecture utilizes the AMOS metacognitive loop. AMOS stands for Discover, Reflect, Apply, Share.
Walk me through that loop. If the AI is asked a legal question, what does AMOS do?
First, the system discovers the new signal, which is the user's prompt. But before it just predicts the next most likely word, it reflects.
It actually pauses.
Yes. It cross-references the potential output against its digital genome to ensure the output aligns with its fundamental commitments to factual reality. If the reflection passes, it applies the change or generates the output. Finally, it shares that updated state with the rest of the system. Crucially, this loop is overseen by what the paper calls cognizing oracles.
Okay, a cognizing oracle sounds a bit mystical. What is its actual function?
It is an internal verification mechanism, and its most vital feature is the ability to abstain.
To abstain.
Yes. If the oracle cannot verify the grounding of a signal, like if it cannot trace a court case back to a verified real-world database, it flatly refuses to process it. It hits a hard stop. It chooses not to guess, prioritizing coherence over fluency.
Okay, I have to play devil's advocate here. Isn't this just slapping a very fancy form of bureaucracy onto an AI? Why do we need digital genomes and oracles? Why not just do what the major tech companies are doing right now, build a massive neural network, feed it all the data on the internet, give it unlimited compute power, and assume that eventually the sheer volume of data will force the model to figure out coherence on its own?
If we connect this to the bigger picture, we run straight into what cognitive scientist Stephen Harnad called the symbol grounding problem.
Oh, I've heard of that.
The paper specifically highlights this barrier. If you just train a model on more and more text, it certainly learns more complex statistical correlations between symbols, but it never, at any point, learns what those symbols actually refer to in the physical world. Scaling up language prediction does not spontaneously generate a mastery of causation or physical consequence.
It makes sense. You could memorize an entire dictionary in a foreign language and learn all the grammar rules for how the words come together. But if you've never stepped foot in the country, or tasted the food, or felt the anxiety of missing a train, you don't actually know what any of it means. You're just matching patterns.
Exactly. What the mindful machine architecture proposes is shifting the fundamental locus of intelligence. Right now, the industry assumes intelligence lives entirely in the neural network's weights, the billions of statistical parameters.
Right.
Dr. Michelini argues that true intelligence lives in a governed network that preserves a system's identity over time. Consider a biological organism. Your individual cells are constantly dying off and being replaced. Your metabolic resources fluctuate. Yet your organismic identity remains intact.
Because it's governed.
Yes. The mindful machine uses the digital genome to preserve the identity and factual commitments of the software, even as underlying language models or data sources are swapped out or updated.
Here's where it gets really interesting for you, listening right now. Because if we actually change how we build AI, moving from a giant statistical guessing machine to this governed self-correcting loop, it means we have to entirely change how we test it. We have to redefine how we evaluate artificial general intelligence, or AGI.
The current evaluation paradigm is fundamentally flawed.
Yeah.
Because it rewards systems that look highly intelligent under isolated, static test conditions.
Right. A new model scores in the 90th percentile on a standardized medical exam, and the media cycle just goes wild.
But those benchmarks completely hide coherence debt. The model can mimic the correct answers on a test, but it lacks the internal governance to survive deployment in an open hospital environment where patient conditions change dynamically.
So the paper proposes a totally new set of criteria for AGI, and this totally flips the script for how we should view AI progress. It means the next time you see a headline about a new AI passing the bar exam, you shouldn't be impressed unless it can demonstrate 4 specific capabilities.
Exactly. First is grounding. Can it connect its symbols to operational reality, not just other words?
Right.
Second is memory. Can it preserve a continuous episodic history without its identity drifting off course over time?
Okay, that makes sense. And then the third criterion is perhaps the most difficult for current models, right? Repair. When the system makes an inevitable error, can it localize exactly where the incoherence happened and correct its own internal model?
Yes.
Because if I realize I have a bad fact in my head, say, I thought Pluto was still a major planet, I just update that one fact. I don't have to relearn what the solar system is. But with a large language model, you can't easily surgically remove one bad fact, right? The knowledge is smeared across billions of parameters. You often have to retrain the whole model.
That is the exact inefficiency. The fourth criterion addresses energy discipline. An AGI must use shared structural knowledge to be computationally efficient.
Instead of burning tons of power.
Right. Instead of using brute force, massive energy consumption to calculate every single step from scratch, it should rely on a governed framework. Under Dr. Michelini's framework, an AGI is not a chatbot that mimics human speech perfectly. A true AGI is a system capable of the disciplined governance of knowledge under lived consequence.
It has to have stakes.
Yeah.
It has to recognize when its map has diverged from reality, and it has to care enough, mechanically speaking, to fix it. This has been an incredibly dense but really rewarding journey. Let's do a quick recap.
Sounds good.
We started with the babble problem, everyone confusing a mere signal with actual structured meaning. We explored how mathematics stabilizes structure, while language acts as an interpretive protocol that actively performs an epistemic intervention on the receiver.
Yes.
We defined the hidden systemic risk of coherence debt, the dangerous gap between fluent output and physical reality. And finally, we explored the engineering response. Mindful machines governed by a digital genome and the AMOS loop, shifting the goal from text generation to self-correcting knowledge.
The transition from static models to governed representations is really the only sustainable path forward if we want these systems to operate safely in open environments.
And the biggest takeaway I want you to leave with today is about your own role in this system. Every time you open up a prompt window and ask an AI for help, you are actively participating in this epistemic protocol.
You are the receiver.
Yes, your prior knowledge, your trust, and your context. You are the one granting meaning to the hollow signals that machine is generating. Which means, right now, you are the one bearing the entire risk of its coherence debt.
Which brings us to a final lingering thought. The paper relies heavily on Wittgenstein to remind us that human meaning is inextricably tied to shared practices. It relies on our form of life.
Oh, that's profound.
So even if we engineer the perfect AGI, a mindful machine with a flawless digital genome, operating the AMOS loop perfectly to monitor its own coherence debt and self-correct, we still have to ask a profound question.
What's that?
Can a machine made of silicon ever truly share our human form of life? Or will it forever be trapped, simulating commitments, fundamentally insulated from the physical, fragile, lived consequences that give human knowledge its actual weight? Something for you to ponder.
Wow. When you look at the vintage watch, you see the gears. When you look at the black box of AI today, you only see the text. But maybe if we follow this governed framework, we can build a new kind of transparency, not of physical gears, but of rigid, observable commitments. Thank you so much for joining us on this deep dive. Stay curious, keep questioning the signals you receive, and we'll catch you next time.